Hello. In the previous lectures, I talked about the concept of cryptography and RSA algorithm. In this lecture, again, I will have a review on basic concepts of cryptography, and then we will see how RSA algorithm works using Python code, and after that we will start talking about another approach for cryptography which is used in different cryptocurrencies like Bitcoin, which is called elliptical curve cryptography. Okay. In this figure, you see the general concept of symmetric cryptography. Symmetric cryptography means that both sides have the same key. For example, suppose that Bob wants to encrypt a message. For example, his message is "Hello Alice," and Bob wants to send the encrypted message to Alice. To do so, if they are using symmetric cryptography, so both must have the same key. Bob encrypts the message with that shared key, sends the encrypted message through the network. Alice, when receives the encrypted message, again uses the shared key, and unlike or decrypt the message. Okay, this is called symmetric encryption and decryption, which both sides have the same key. It's a very old approach from 1970. Some other stronger approaches, which is called asymmetric cryptography, are used. So from 1970, okay? Asymmetric approaches, the general concept of asymmetric approaches is that everybody must have two keys. One public key, another one private key. So everybody has two keys, public and private. Public key is public. It means that everybody can see what is the public key of Bob, what's the public key of Alice, what's the public key of Eve. So public keys are publicly available. Everybody in the network knows the public key of other persons, but the private keys are secret. The private keys are secret. Only the person who is the owner of the private key knows what's the private key. For example, Bob knows his private key. No other person can see his private key. Only Bob knows what is his private key. And Alice The only person who knows the Alice's private key is the Alice. She knows what's her private key. Okay, so public keys are public. Everybody knows other person's public key, but only the owner knows what is his or her private key. Okay? Keeping this in the mind now, suppose that Bob wants to send a message to Alice and wants to encrypt this. Again, hello Alice. Has the Alice's public key. Everybody has the Alice's public key. So Bob uses Alice's public key to encrypt or lock the message, okay, and send it through the network. Alice receives the encrypted message. Also, other persons in the network may receive the message. But who can unlock or decrypt the message? Since this message was encrypted by the Alice's public key, so only the private key of Alice, can unlock this message. Who has the private key of Alice? Only Alice. So only Alice can unlock the encrypted message with his private key, and this means that for encrypting and decrypting messages with any algorithm, RSA, elliptic curve, or any other asymmetric algorithm, the sender must lock or encrypt the message using receiver's public key, and the receiver can unlock or decrypt the message with his or her private key using public key of the receiver for encryption. Then the receiver uses his or her private key to unlock or decrypt the message. Okay? This is called sorry, this was the figure. As you can see, this is called encryption. Bob uses Alice's public key to encrypt the message, and Alice uses her private key to decrypt the message. This is called encryption. Another application is authentication in this figure. I want to send a message to you. I'm going to say, for example, next week we will have an exam. Suppose that the environment is not safe, so someone else maybe can pretend he's me and send such a message behalf of me. Okay? How you can be assured that this is Wahid? How? So again, I want to send you a message and I want you all be sure that's me. To do so, To do so, I encrypt my message with my private key. So everybody who has my public key, and everybody has my public key because I said the public key is public and everybody knows other person's public key. So since you all have my public key, so you can simply decrypt my message. So I encrypt my message by my private key, send it to you, and all other person can decrypt the message and read the message. This is not encryption, because when we encrypt the message, usually we have one receiver. But in this case, when I encrypt the message with my private key, all other persons can decrypt it. This is not encryption. This is just to prove that it's me. This is authentication. Why it's authentication? Because when they decrypt the message with my public key, it means that someone else, it's me, someone else encrypted it with a private key. Who has the private key? Only I have the private key. So all the persons can be ensured that who was the sender, and this is called authentication. So when you encrypt the message with your private key, this application is called authentication. And in fact, it's digital signature. Okay, it's something like digital signature. It seems that I signed the message. Okay, that's me. This figure shows both authentication and encryption. Not only we want to send the message encrypted, but also we want to receiver be sure that who was the sender. To do so, suppose that Bob wants to send a message to Alice. So at first, Bob encrypts the message with his private key at first. Okay, Bob encrypts the message with his private key, and then this encrypted message again is encrypted by Alice's public key. And then Bob sends this twice encrypted message to the network. Alice receives the message. Now, Alice at first uses her private key to unlock the message. Then again, Alice uses the Bob's public key to encrypt the message, and now she knows what's the content of the message, and she's assured that who is the sender of the message. Now, let's see these concepts through the RSA. In the previous lectures, I explained how those pieces of codes in Python works, but since most of you requested and most of you had some problems with working with those codes, so again I explained those codes with more details. So just a moment, please. let's share my screen. Okay, that's it. As you can see, this first part, this first of the code generates private and public keys. Okay, here this part generate the private key. So private key is an object containing the private key. This command prints out the private key onto the screen here as the output of the program here. This part, okay. This print command prints the private key like here, but usually we use public and private keys using some files. So this command save this private key to a file named RSA key. Let's put another name, for example, Bob private key. Okay, then this command generates a public key for this private key and store it in the public key. So public key now is an object associated with that private key. This command print out the public key. So this is the public key here. This is the public key. Okay. This is the private key. It should be kept safe. Nobody must have access to this private key, and you are the only person that can have access to the private key. But this public key can be public key. You can send this public key anywhere you want, and this command save the public key to the file. Let's change the name Bob public key. Okay, each time you run the program, this program generates different private and public keys. So if you run it twice, this is Bob. This is Bob. So if you run it twice, the new private and public key was rewritten in the previous file. So just run straight one time, then find the place in which these files are stored. Users, admin. This is the place, the default place of the Python, at least in my system. So now I should find the Bob public key and Bob private key. So this is Bob private key. This is Bob public key. So now I copy and paste them in a safe place. For example, in my documents. Okay. And you should keep them safe. If you want to send someone encrypted message, you must have his or her public key. Okay, now we have the public and private keys. The second part here, that's me. This part, okay? Let's put it at the end. This part, you write your message here. For example, I want to encrypt this message and send to someone. Hi, are you working? If it's the case, what's your job? Then to encrypt this, you must use the receiver's public key, which we saved it in a file. For example, suppose that I want to send this message to Bob. So, what was the name of the Bob's public key? Bob public key, okay? And that's it. This command printed out the encrypted message. So if I run the message, this is the encrypted message, okay? Now we have an encrypted message. We send it to the Alice. And now how Alice must decrypt this message? See here. I use this part of the code. I use this part of the code. I cut it to put it here. At first, I must have the private key. What was the private key? The private key was Bob private key. So I open the private key I must put the message here. This message I copy. It was the encrypted message. So I have the encrypted message. I copy the encrypted message. I put it here. I paste it. So this is exactly this encrypted message. I put in now X is the encrypted message. Using this command, I decrypt the X, the encrypted message, and then I print it out. Let's print it out. I run the program. This is exactly the original message. Hi, are you working? If it's the case, what's your job? So you can use these programs simply to encrypt the decrypt message. And the last thing, which is also very important, this part, this simple part, this generates a digital signature. If this is my message, I want to sign this message. I want to everybody knows that it's me for authentication. So I have a message for digital signature. I use the private key, but what's the private key? Again, for private key, you can use this part of the code. Okay. So I read the private key from this file, and Alice private key is an object showing that Bob private key, but maybe it was better that the variable name was Bob private key. Okay, who cares? It's not important. And now Alice's private key sign this message. Okay. This is the signature. This is the output of the program. This is the signature. And now you can verify it. How? I copy the signature. I put the signature here in another one program. Using the public key associated with that private key, I can simply check. If everything is okay, there is no output. As you can see, this program has no output. But if there is a little bit, a change in the message or a change in the signature, invalid signature, this error will be shown. If I correct it again, okay, now there is nothing. Or even if you change a bit, in the signature, you will encounter an error. So again, in this lecture, I explained how we can use these RSA libraries to encrypt, to decrypt a message, to generate public and private key, and finally to sign a message and to verify a message. This last part, verify that the message and its signature both are consistent or not. Okay. And now let's have a review on another approach for decrypting message called elliptical curve. In the previous lecture, I have a short introduction to elliptical curve. Now, let's watch a short video introducing what's elliptical curve. Let me run the video.
In Bitcoin is in many ways more powerful than RSA. We've learned about public and private keys in general.
Okay.
We've learned about public and private keys in general. We've learned how we can use the public key to encrypt something that can only be read by somebody else. We've learned how we use a private key to sign something so that everybody knows we've sent it. More on all of this in the details of Bitcoin to come. We've also learned about a particular algorithm, which is called the RSA algorithm. And the RSA algorithm is probably the most used public key algorithm in the world. And we learned about how to do it. And I'm hoping you've done an example, and you may even have looked at my proof of it. Okay, so we know everything there is to know about RSA. We are now RSA experts. RSA is not the algorithm that is used, the public key algorithm that's used in Bitcoin. The public key algorithm used in Bitcoin is called elliptic curve cryptography, or ECC, and we're about to learn about that. So that's what this lecture is about, and we're going to learn about elliptic curve cryptography. So obviously we know something about cryptography, but we don't know anything about elliptic curves. Some of you might, but I'm assuming you don't. So the way this lecture is going to go is I'm going to talk about how we can use the kind of cryptography that elliptic curve cryptography is by teaching you what the discrete logarithm problem is, what that is. And then we're going to look at the specific example of a discrete logarithm problem that has to do with elliptic curves. So we learn about the discrete logarithm problem, which is something that we can do with any abelian group. And again, we're going to learn what an abelian group is. And then we're going to talk about elliptic curves as a particular abelian group that gives us a particular cryptography that's used for Bitcoin and lots of other things. It's actually a very, very powerful way of doing encryption. In fact, it's in many ways more powerful than RSA. Okay. So that's a lot to do in one lecture, so let's get to it, okay? So, right. Okay, so I'm going to introduce an operation called dot. Now, we're going to learn about dot for elliptic curves eventually in about 10 minutes. But for now, I'm just going to tell you that it's a dot product. I'm going to tell you some properties it has, okay? And we'll do that with the elliptic curves in about 10 minutes, as I say. Okay, our dot product is going to be based on elliptic curves, and it will not be defined for all real numbers. It will be defined only for real numbers that lie on the graph of a particular curve, which will be an elliptic curve. Elliptic curves, there's two kinds of graphs. We'll see pictures in a bit, but the main one is, it looks something like that. Can you see that? I don't know. Anyway, it does. I should probably draw it with, but we'll see them. Don't trust me. We'll get there. Okay. So we have. It's only defined. So this operation is only to be defined on points on the curve, and one extra point, which is sort of point at infinity. We'll call the point at infinity 0 for good reasons. Okay. Now, this dot product that we're going to define will have the following properties. First of all, the 0 is going to operate like an identity in addition, a 0 in addition, not a multiplication. It's a bit confusing with the notation because dot looks more like multiplication than addition, but you'll do better to think of it as addition, at least so far. So a plus 0 is a dot 0 is a, same thing with 0 dot a, okay? That says that we've got an identity element, okay? Dot is associative. That means that if I've got 3 elements, I can dot, and I'm dotting them, have dots between them, I can dot from either a dot b, and then c, or a and then b dot c, and I get the same answer. What that turns out to mean is that if I've got n of them, if I've got a string of them, I can bracket them in any way I want. I can do them in any order, but I have to keep them in place so far because I don't know that turning them around won't change anything. But I'm getting ahead of myself. But I can just bracket it anywhere. I can do them in any order I want. And then the other thing is that, and this is part of the use of the identity. You've got an inverse. So for each a, there's something that acts as minus a, such that a dotted with minus a, I think you get a plus at the moment. What's a plus minus a? It's 0, right? So the same thing happens here in general, okay, with this dot product. Okay, now these properties are what make up what mathematicians call as a group. This is a group. The only other thing you ever hear anybody talk about in terms of groups, sometimes they say there are 4 axioms, and the other axiom is that it's closed under the operation, which means if I take 2 elements of the operation and I apply the 2 elements of this set and I apply the operation, I get another element of the set. I'm taking that as read. That's true here. We're only defining it on where it's defined, and so we're going to define an operation on elliptic curves that when I do the operation on 2 points of the elliptic curve, I get another point of the elliptic curve. Okay, and this is all called a group. That's the group properties. There's lots of groups in the world. So, for example, modular or the modular numbers, mod any number is a group. All kinds of things. Matrices under multiplication is a group. Matrices under addition is a group. Lots of things are groups. When I say matrices is a group, the invertible matrices is a group. That's not all matrices. So we're not talking about matrices now, but just to make that clear, if you want the group of matrices under multiplication, you have to restrict yourself to the ones that have inverses. Okay. Forget I mentioned it. Okay, but the dot product we're going to talk about has one extra property that not all groups have, and that is called commutativity. And that says that A dot B is the same as B dot A. Now, this isn't the same, for example, of matrices. So matrices, say invertible matrices as a group, but they don't have this property that if you multiply them A1 times A2, whatever, you get the same thing as A2 times A1. In fact, with matrices, you don't even necessarily get the same shape. If A is a 2x3 matrix and B is a 3x2 matrix, AB is I think if I remember this right, which way I said before, is a 2x2 matrix and BA is a 3x3 matrix. They're not even the same size, let alone the same matrix. So matrix multiplication does not have this property. Under some circumstances, it has all the other properties, but there are certainly groups of matrices, but you have to take particular sets of matrices and then they form a group. Not going there now. So it's not true of every operation that works like this. Another operation that doesn't work like this is subtraction, right? A minus B is not the same as B minus A. That's, I guess, an easier one. So not all operations are commutative, but the dot product we're going to show you in a bit is commutative. Again, a mathematical word here, a phrase or name. If you've got a group and the operation is commutative, it's called an abelian group. It's named after a mathematician called Abel. It's called an abelian group. And in fact, when I was a young mathematician many decades ago, it was a great joke. One of the few mathematical jokes was what's purple and commutes? You know, just abelian grape. So now you get that great joke. Okay, so we're going to make a one-way function. Of course, that's where we're going with this. We're going to have if we're going to make a public key cryptography, we need a one-way function. And here's the function. And this is going to work with any abelian group. Okay, given a point P and a number K, we can compute P times P times Pk times, right? So that's perfectly reasonable. And so we call that P to the K. This is where the notation goes a bit funny because we were thinking of addition before, and then we're sort of thinking multiplication, but we call that P to the K. That's why I don't use the plus sign. Some people use the plus sign for the elliptic curve, the product I'm using the dot for, because it has all these nice abelian group properties. And people often use plus signs for abelian groups. But then I want to talk about this, and it goes awry here. So that's why I'm using dot, which is a neutral plus and addition. So here I'm thinking a bit more like plus and multiplication. Here I'm thinking a bit more like multiplication. So choose P dot P dot P dot P K times. I'm calling that P to the K. Okay, you can handle it. And that's easy to compute, assuming that the matrix, the group properties, the operation is easy to compute, then it's easy to compute K times. That's fine. Now the discrete logarithm is a problem I mentioned at the beginning of the lecture, and the discrete logarithm is this. Given the Q up here, how do I do this? Let's see if I can do it. It doesn't quite work. Okay, given the Q, here it is. Given the Q and the P, find K. Okay, so if I'm given P and K, finding Q is easy. Given Q and P, that's going in the other direction, is hard. That's a hard question. Okay, in some groups anyway, and certainly in the elliptic curve group we're going to talk about. The reason it's called a logarithm is it's what we generally have with multiplication, right? 2 to the 5 is 32 is the same thing as saying log base 2 of 32 is 5. So that's the same idea here, right? Okay, so we want to know what the K, we're trying to find the K, which is the 5 here, right? If we know that the Q is the 32 and P is the 2. Okay, so logarithm is undoing exponents. P, this is an exponent. We want to undo the exponent. That's a logarithm. So that's the problem. And this can be done with any abelian group. That's always called the discrete logarithm problem. And that's the one-way function that we'll be using. But now we're going to talk about the particular dot function operation we're talking about, which comes from elliptic curve. So what's an elliptic curve? An elliptic curve is a graph of an elliptic function. An elliptic function is I got ahead of myself. An elliptic curve is a graph. An elliptic function is a function that satisfies this equation for some A and B. Okay. We're going to now turn to a graphing calculator and look at what this looks like. Okay, here we are at the calculator, as promised. So what are we trying to do? We're trying to graph y squared equals x cubed plus ax plus b. Okay, now it can't do that yet. It doesn't know anything about a or b, so I'm going to add a slider for b and a slider for a. So now it's got an answer. Okay. So that's an elliptic curve. I can get slightly different shapes by messing about with a and b. So let's slide a around a bit. So a is the one we multiply by x. Now, I thought that was fun. Look what happens. It's kind of like a ghost on its side, isn't it? And then I do this, and suddenly at some point, whoops, it becomes disjointed. But even when it becomes disjointed, it's still useful for us. This is also either in its joined up form or its disjointed form. It's fine for what we want to do. And again, we can do that. So you can see these are what elliptic curves look like. People usually draw ones that look like this, and probably not looking quite so steep. And we'll see pictures. Okay, so that's what elliptic curves look like. So we look at an operation on points in elliptic curves. Okay, so we now know what an elliptic curve looks like. We still don't know what the dot product is, or the dot operation is. We're about to find that out. Okay, so now, not nearly as nicely as the graphics calculator, certainly not as accurately. I'm going to draw for us. You ready? We're going to draw an elliptic curve. I'm going to do something like this. Okay. And one thing I want to say about this elliptic curve, and this is true of every elliptic curve, this is the x-axis. It's symmetric about it. Okay, so all elliptic curves are symmetric about the x-axis. And why is that? Because they're y squared equals something. So obviously, if all of this comes out to be minus 3, if y was going to come out to be minus 3, then y squared would be 9. If y was going to come out to be 3, then y would also be 9. Y squared would also be 9. So that's what happens. So this is symmetric, and that's really important in the geometry here. I'm now going to do with nice purple points. I'm going to do a or p plus q, say. There's P, there's Q. Okay. So my picture doesn't help me much here. Let me see if I can get back to that other color. I don't know what color this is. Not quite right. But what I do is I take, it's a geometric thing, and I'm going to have to get out of the way. I'm in the way here. I can see that. And I'm going to take the line from P that goes through both P and Q, and it's going to hit the curve at a point. It doesn't always hit the curve at a point. It most of the time hits the curve at the point, and we will look at the examples where it doesn't in a minute. So what we then do, though, is, let me get back to my purple. This point is not the dot. What we then do is we reflect this up, and this is why it's important that this is symmetric. And this is the point P dot Q. Okay. So what you do is you take the line that connects P and Q, you find out where it intersects the ellipse, assuming it does intersect the elliptic curve, and where it does, you flip it either up or down across it around the x-axis. Okay, that's P dot Q. So let's look at a couple of things. Well, first of all, it's quite clear that this is commutative, because the line between P and Q is the same as the line between Q and P, and various other things are pretty clear too. Now, let me look at what happens when, let me go back to my gray, I'd like that gray. When does it happen that it doesn't intersect at all? Now, this is true if the elliptic curve is disjoint, as we had shown before, or joined up. In either way, this works the same. So when is it that P and Q, the line between them doesn't hit the axis of the elliptic curve again? It's when it looks like this. It's when the line between them is vertical, okay? In that case, we think of the point that they meet at is this point at infinity that we call 0. Okay, so what does that tell me about this point Q compared to P? Well, it tells me that P plus, so what is P plus Q? Well, 0, because 0 flips itself to 0. So P plus Q is 0. So Q is minus P. So, and P is minus Q, so it's symmetric in that way. And so the minus is just flipping across the axis, okay? Okay, now, right, okay, so that's all good. Okay, so, okay, I hear you asking yourself, hold on a second. That's all well and good, but the way I have to start this is I have to do P dot P dot P, use a bit P purple, etc. So I have to start with P dot P. Well, P, back to purple, P is 1 point. What do I do with 1 point? Okay, so how am I going to do P dot P to begin with? And what I do is I draw the tangent line. This is the, it didn't quite work, but this, trust me, this is the tangent. Okay, so that's a tangent line to the curve, and that meets the curve in one other place. So this down here is P dot P. That's what P dot P is. Once we've got that P dot P, we can go to P dot P by taking that line and seeing where it intersects. I think it will be set all the way down that way.